See in physics. You do like that.
All right. Let's do notes for 4.1 first, and then towards the end of the class, I'll check your homework. You just have to finish page 3 and 4 from your test review. I'll go over a couple of practice problems in preparation just for tomorrow's test. But tomorrow your test will cover Unit 3, but also Unit 2 is kind of built into it. So power rule, product rule, quotient rule, derivatives of trig, and then all of Unit 3, which so chain rule, implicit, derivative inverse set of points, inverse trig functions, log derivatives, log differentiation. All right. So today, just want to talk a little bit about interpreting derivatives, and that when we see f prime or g prime or p prime, it's always talking about some sort of a rate, some sort of a kind of like a moving value. And then we'll talk a bit with particle motion. We saw a little bit of this already from Unit 2, but just want to extend this a little bit more. So slope between 2 points, we know this is just simply change in y over change in x. You're changing your dependent variable. So delta just means change, and then change divided by change of your independent variable. So your derivative of f is going to be your unit for f, which is usually y, divided by the unit for x. If f prime is greater than 0, we know that that means my f of x is increasing. It's going to exhibit a positive slope if my f prime is greater than 0. If f prime is less than 0, then my function is going to be decreasing because my graph is going to be exhibiting a negative slope. Mr. Sullivan wants Mr. Bruce to finish creating his packets in Algebra 2. The number of packets he has completed is modeled by P of W, where W is measured in weeks. Interpreting P of 10 is equal to 1 in the context of this problem. But this is more of a static value. This is not prime. So we know that that means after 10 weeks, Mr. Brust has completed 1 packet. Interpret P prime of 39 is equal to 4. So now this is talking about the rate at which he is completing his packets. At 39th week, his rate is increasing by 4 packets per week. So anytime you see a prime, you just have to be able to phrase it involving rate. Okay, try number 2, A and B. See if you can distinguish the difference between a B of 3 versus B prime of 4, and be able to phrase it in a way that can explain the context of that notation. Now, B of T in this case is already a rate. So in the third year, Mr. Kelly is buying cars at a rate of 150 cars per year. B prime, we know that's going to be a rate of a rate. But we don't want to say rate of a rate. We want to say either the rate is increasing or the rate is decreasing. In this case, that 10 means the rate is increasing. A -5 would mean that the rate is decreasing. On the fourth year, the rate at which Mr. Kelly is buying baseball cards is increasing by 10 cards per year squared, or 10 years per year per year. Okay, try 1 and 2, see if you can write out the meaning of those notations. So G prime of 1 would indicate, that 1 indicates the amount of time that has passed in terms of hours studied. And then if it's G of 1, it'll actually tell you the grade, but it's actually for G prime of 1 is that, after 1 hour studying, how much will the grade improve? That 3 is now a rate. So 3% per hour. Number 2, also a rate. After 15 minutes, the distance from home is increasing at a rate of 650 meters per minute. All right, page 2. We have position function, which indicates the position of the ball after it's thrown up straight up in the air. So we can see that the position of the ball is going to be, as time passes, is going to eventually reach that max height close to 20, but then after time continues to pass, it's going to eventually make its way down to the ground. The velocity is going to be a linear because you have a parabola, which is x squared. The derivative of x squared gets you down to x. The derivative of x gets you down to a constant. So position, velocity, acceleration, it's going to be in that derivative relationship. But then graphically, the derivative also makes sense, right? If I start off with the quadratic, the derivative of this will turn into a linear, and then linear's derivative will turn into a constant. So velocity can be thought of as v of t, or it can be thought of as the first derivative of position, if position is s of t. But there's a lot of different variables for position. Sometimes you may see s of t, sometimes you may see h of t, sometimes you may even see p of t, you may see x of t. So there's a lot of different common variables that problems use for a position function. Acceleration, you can think of that as the second derivative of your position, or you can just think of it as one derivative down from their velocity function. Velocity is the rate of change of position. So if v of t is less than 0, that means my position is decreasing or moving to the left. So typically, with particle motion, we're moving left and right along the x-axis. So negative velocity usually means left, moving left. Positive velocity usually means moving to the right. And then if you're at rest, that means you're not moving, which means velocity is 0. Average velocity is defined as the change in position divided by the change in time. Just be aware that when students see average velocity, typically tendency is wanting to use the velocity function because you see the word velocity, but average velocity doesn't use the velocity function. It uses the position function. It's the slope of the position. Now, if it's asking for the instantaneous velocity, then you would use the velocity function. Right? Speed is the absolute value of velocity. So speed is always a positive numeric value. Meanwhile, velocity can be negative. Okay, if velocity and acceleration have the same signs, the particle is considered to be speeding up. If velocity and acceleration have opposite signs, then speed is going to be decreasing, or the particle is going to be slowing down. So here are some examples. The first example, at time t equals -5, my velocity is 3 and my acceleration is -4. Opposite signs, what does that indicate? That means my speed is what? Slowing down, right? Decreasing. Speed is decreasing. Second example, at t equals 1, my velocity acceleration, one is -2, the other is 7, still what? Obviously still slowing down. At t equals 2, my velocity is 1, my acceleration is 0.1, so therefore speed is, speeding up or slowing down? Speeding up because they're both positive, right? Okay. And then at t equals 4, -1 for velocity, -1 for acceleration. Still speeding up, yeah. Displacement is just the net change in position. It's just S of B minus S of A. that just means where you are in relation to where you end up in relation to where you are. So sometimes if you end up to the right of where you are, then your displacement is positive, but it's okay to get a negative displacement. That just means you end up to the left of where you started. A similar question is velocity increasing or decreasing at t equals 1? So at t equals 1, if we know that velocity is -2 and acceleration is 7, is velocity increasing or decreasing? You may be looking at that -2 and wanting to look at the velocity to determine. But whenever you see the fact that you see the word increase decreasing, that those two words are changing what we're asking about. This is no longer asking about velocity, it's asking about the rate of change of velocity. So if it says, is velocity increasing or decreasing, you're just looking at the acceleration. So in this case, my acceleration is +7. So since acceleration is positive, my velocity is increasing at t equals 1. All right, let's work through an extended problem here, page 3. So the problem reads, the position of a particle moves along the x-axis, modeled by x of t. Find the displacement of the particle during the first 2 minutes. So, displacement is just change in position over change in time. So find x of 2, find x of 0, and then you're just going to subtract it. So your displacement formula is just x of b minus x of a. Number 2, find the average velocity. I know that the tendency is you see the word velocity and you want to use the velocity function, but average velocity is just the change in position over the change in time. So we don't use velocity for average velocity. So it's just the slope of your position at 2 different points. So x of 2 minus x of 0 over 2 minus 0. Now look at how much displacement and average velocity look alike. Displacement has no time component. It is just the change in position. But average velocity, we do have a time component. It is a rate. So we do need to make it into a fractional relationship there. Any questions with 2? Number 3, find the velocity of the particle when p equals 4. Now it's asking for the instantaneous velocity at a moment in time. Now we can use the velocity function. So velocity is the derivative of position. So find v of t, and just plug 4 in. Your units will still be centimeters per minute. But now it's asking for an exact value at a specific moment in time. Next up, find the acceleration. Acceleration is another derivative down. So find x double prime of t. And then plug in 4. Your units will change as well. It's a rate of velocity. So it's centimeters per minute, or centimeters per minute squared. Speeding up, slowing down, increasing or decreasing speed. For number 5, we want to ask, is the particle increasing or decreasing speed? We have to compare signs. So at t equals 4, we have the data that we need. We have the velocity at 4, we have the acceleration at 4. They're both the same signs. So that tells us our speed is increasing. Yeah.
When number 4 is the minutes always going to be squared like acceleration?
Yes. Yeah. Because essentially what's happening is velocity is centimeters per minute. And if you're doing another rate on top of that, ends up being centimeters per minute, and then that reduces to be centimeters per minute squared. Okay, next up, particle motion from a graph. The figure shows the velocity graph. So this tells us how fast the object is moving at any moment in time. So just want to have us kind of label this accordingly. So in this case, whatever's above the x-axis indicates positive velocity. So we can tell that here the object is maybe slowing down, the velocity is decreasing, but it's still a positive velocity. So we're still moving, in this case, to the right. But then at a moment in time, it's going to end up stopping completely, changing direction, and then getting down to negative velocity, it's going to speed up, speed up. It's going to reach its highest velocity at t equals 2, and it's going to slow down, stop, turn around, move to the right again, speed up, slow down, and then it comes to another stop. So just want to kind of have some visual connection in terms of the object moving along the path of that graph. So number 6 says, when is the particle moving to the right? So when would you say particle is moving to the right? From where to where? This interval, right? What interval is that? 0 to 1. And then from, that's an estimation, right? If you had to guess, where's that decimal? Yeah, 4.7, 4.8. It doesn't, if you're asked to estimate, then it doesn't really matter what that value is as long as you are in the ballpark range. So 4.8 all the way to 7, right? Next up, what is, and then our justification is because velocity is positive. So that indicates we know moving right. When is particle moving to the left? It's going to be this interval here, right? From 1 to 4.8 or 4.7. Think of acceleration as the slope of velocity. So basically, when is particle's acceleration positive? Another way of asking, when is the velocity going to have a positive slope? So acceleration is positive in this interval. And the negative acceleration, again, acceleration is the slope of velocity. So negative acceleration will be in this interval wherever there's negative slope. Oops. It's negative from 2 to 6, or positive from 2 to 6, negative from 0 to 2, and 6 to 7. And then is the acceleration ever 0? It's never 0 because the slope of my velocity is never 0. When does a particle have the greatest speed? So speed is the absolute value of velocity. So greatest speed is going to be at t equals 2. And at t equals 0. So these two moments in time, we have the greatest velocity. When is a particle speeding up? This is when your velocity and acceleration have the same signs. So either both are positive or both are negative. So I think in this interval here, I have negative velocity and I have a negative slope. And in this interval here, I have above the positive velocity, above the x-axis, and then positive acceleration because of slope. and it's slowing down. This is positive velocity, but negative acceleration. Here, negative acceleration, negative velocity, but positive acceleration. And then over here, negative negative acceleration, but positive velocity. So whenever the signs are different, you're going to be expecting decreasing speed. So your homework, just page 1 through 4. This will be due on Wednesday, since tomorrow you guys are going to be preparing for your, you'll be taking your test. If you guys get out a sheet of paper, let me highlight a couple of things for tomorrow's test. One is being able to understand when to use log differentiation and when to use power rule, when to use exponential rule. So just want to highlight some distinction here. If I have a variable raised to variable, like x to the cosine of x or cosine of x to the 5x cubed, these we don't have specific rules for derivative wise. So we have to put it into a different form. And these are problems where we got to go through log differentiation. Same thing with this one here. Y equals x to the natural log of 2x. These are log differentiation problems, which means we'll practice some of them. That means we got to take the natural log of both sides. Then we got to use log properties to bring the exponent down, and then we go through product rule. Meanwhile, if I have a constant raised to a variable, like e to the x to the 4 or 4 to the 3x, these are exponential rules. So exponential rules, this is e to the u times u prime. This is a to the u, so a to the u is natural log of a times a to the u times u prime. Meanwhile, if I have a variable raised to a constant, that is power rule. That's just like 4x cubed. So they all look kind of similar because they all involve a base and an exponent, but depending on which is a variable and which is a constant, that's going to determine what rule you're going to use. So can we put this down here and try this one here? And maybe we can try all these, just because these are the ones that take the most work to set up. But let's start with this one here. Y equals x to the natural log of 2x. The first thing is recognizing, okay, this is not power rule. This is not exponential rule. This is a variable raised to variable. I can't work this problem unless it has a different form. So I got to take the natural log of both sides. once you take the natural log of both sides, the exponent is free to come down. Once it comes down, then it turns into a variable times a variable. We got to go to the product rule. Try that. Bring that y back over to the right side and then replace the y in terms of x. Okay, let's try this one here. X to the cosine of x. I just saw a opportunity to clean this up, but you don't have to. I saw sine over cosine is tangent. I made that replacement. Okay, a little bit of time here. Let me create a problem that we can maybe practice our derivative rules here. Try this one here.
Yeah.
So make sure you review your derivative rules, right? So the back of your packet, back of your notes packet and the test review packet, we need to make sure that we have these derivative rules down. So you got the 6 trig, you got two logs, you got 2 exponentials, and then you have 6 of the arc trig rules. But again, once you know these 3, you know these other 3 are just variations of the original 3. Okay?
Oh, you're right, but I really get
Vortex, yeah.
No, I'm telling you, like, you're actually gonna like throw yourself. Yeah, you're right. I was. Like I wish someone told me like, yeah, my head's straight. Everything's. Let's do it in 5. What's like, don't get mad. I get like I get it. Right. What am I gonna do? Yeah, like. Them big side. Your suits all to the side. They don't even cover.
So happy with the.
Yesterday. I said something. Really? We've been here. So how close did you go to Karate Bros too? No, I was really sick. I do like guys. Yeah. My dad first.
It's not even that, it's fantastic.
I was like, that cake that you get. Be gone.
It's like, bars, we get a lot of partial. Just doing everything at the same time.
Yeah, I'm just gonna get another sheet of paper and check everything.
Yeah, that's what I do.
That's not.
Might eat that back.
Yes, bro. Even getting all day looks good. You are.
Because that paper pushes out.
Oh, okay.
It's